All right, hello everybody. Hope you're all doing well. We're going to get into our newest lesson on physics after our quick little break there with the plant systems quiz. Getting into actually the harder part of physics here, which is us talking about our next concept, which is acceleration. Okay. Now, all the types of motion we've talked about, whether we were talking about vectors or scalars, it doesn't matter. Everything we talked about was uniform motion, meaning that, of course, everything was traveling in one direction, not changing direction at all, and traveling at a constant speed. So now when we're talking about things moving with acceleration or accelerated motion, that's a type of non-uniform accelerate or motion, meaning that the object is changing its velocity and or its direction while it's traveling. Now, in Science 10, we're going to focus mostly on things that are changing velocity. Direction comes up more in Physics 20, but we can still have things like slowing down, stopping, and then reversing, and that's still a change in direction and a change in velocity. All right? So acceleration as a measurement, as a unit in science, is a measure of how quickly something's velocity is changing. So how quickly is it speeding up, or how quickly is it slowing down? And if you remember our talk about vector measurements, acceleration came up as one of the vector measurements. So we need to keep direction in mind with it. That means that our acceleration can be positive or negative, which can be a little bit confusing because what you might think is positive acceleration and negative acceleration are probably different than they actually are, and we'll cover that in a little bit. But the big thing to focus on right now is that when something is speeding up, it means it's getting faster. What that means for us in terms of its velocity is that its velocity, the magnitude of its velocity, is increasing. In other words, the number that velocity has is getting further and further from zero. So something is speeding up if it goes from like 5 meters per second to 10 meters per second. Okay? That's speeding up, obviously, because our number gets bigger. Something is going faster than it was before. But we can also have something speeding up if its number is becoming more negative, right? So I can have something that's going negative 5 meters per second, right? That just means it's going to the left at 5 meters per second, and that can speed up to negative 10 meters per second. Okay, so in both cases, we're having something speed up. In the first case, in green, it was speeding up to the right, let's say, meaning it's getting faster and faster as it heads right. In our yellow here, it's getting faster and faster to the left. Remember that negative just tells us direction. So that's the reason we throw the word magnitude in here, because we're just talking about the number. Is the number getting further from zero or not? Okay, so then when something goes down or slows down, the reverse is true. The number gets closer and closer to zero. So in this case here, if I just erase my arrow and flip it around, if I have something going from negative 10 meters per second going to negative 5 meters per second, that means it's slowing down, right? The number is getting closer and closer to zero. Zero would be stopped, okay? Similarly, if I had, let's just clear this out of here, if I had something that was heading in at 8 meters per second and it slowed down to a speed of 2 meters per second, we know intuitively that it's getting slower. So I find that students do pretty well with this when it comes to positive numbers, but the negative ones sometimes trip you up. So remember that the negative and the positive is just telling you which direction it's moving in, right? If the number is getting closer and closer to zero, the object is slowing down. If the number is getting further and further from zero, it means it's speeding up. It doesn't matter if it's becoming more negative or more positive. Okay, so this is one of the things about acceleration that's quite confusing for students is the idea of positive and negative acceleration, all right? And so the biggest thing to remember with this is that in physics, whenever we have a positive or a negative, whenever we're talking about a vector measurement, those two things just tell us what direction the thing is either moving in or where it's located. And with acceleration, what positive and negative acceleration tell us is which direction the velocity is changing in. As in, is the velocity becoming more positive over time, or is it becoming more negative over time, right? So really, the tough part here is that intuitively, you think that positive acceleration means speeding up, and negative acceleration means slowing down. That seems to make sense easily in our brains, and sometimes that is true. But the bigger thing here is that the positive or negative sign just tells us which direction the velocity is changing in. And so is it becoming more positive? Is it becoming more negative? Is it speeding up to the right, or is it speeding up to the left? It's kind of the idea. So objects can show positive acceleration in two cases. And the first one makes a lot of sense, and students usually pick up on this one really, really easily. So an object it has positive acceleration when it speeds up in the positive direction. In other words, if I'm going from 10 meters per second to 20 meters per second, see how my velocity is becoming more positive? It started at positive 10 meters per second and now it's positive 20. It's pretty intuitive that it's speeding up because we're increasing the number. It's getting further from zero, and it's increasing in the positive direction. It's becoming more positive over time. So this is showing us positive acceleration. What doesn't make as much sense, which is a little bit weirder for students, is this second case here. So if an object slows down in a negative direction, in other words, its speed is becoming less negative over time, that is also a form of positive acceleration. So to give you an example, let's say I have an object that's going at negative 10 meters per second. Okay, so it's heading to the left at 10 meters per second. Then the object slows down to negative 2 meters per second. Okay, this is still positive acceleration. Okay, it slowed down, right? Its velocity became closer and closer to zero. Okay, but because its velocity is now less negative, or another way of phrasing that is that it's becoming more positive, it's getting closer and closer to the positive numbers, that means it's a form of positive acceleration. All right, you can kind of think of it like a number line, where if I'm moving from negative 10 to negative 2, I am moving my line to the right. The right is the positive direction. Okay, so it's a little bit weirder, but if something is moving to the left and slowing down, that is a type of positive acceleration. Okay, now something can show negative acceleration in two cases, which are really similar to the ones we just saw. So if you think about the term negative acceleration, again, all that means is that the object's speed is becoming more and more negative as it moves, all right? So in the first case here, if something is speeding up in a negative direction, that is negative acceleration. So if I'm going from like negative 10 meters per second, don't know why I like to start there, and its speed changes to negative 20 meters per second, we know that it's speeding up because the number is getting further and further from zero, just like it did here. But it's speeding up in the left direction. It's speeding up in the negative direction. Its number is becoming more negative over time, and therefore, this is negative acceleration. And I find students do a good job with that one too. It's pretty easy to remember, okay, if I speed up to the left, that is still negative acceleration. The last one here is kind of like our second example. It's kind of like this one, all right? So it doesn't seem to make a ton of sense until you really look at what the numbers are doing. So in the second case, it slows down in a positive direction. What that means is, let's say I start at 20 meters per second, positive, okay? And I change speeds to 5 meters per second, okay? I slowed down, right? My number got closer to zero. It's still a positive speed, but that's okay because my speed is becoming less positive over time. In other words, if something is becoming less positive, that's the same as it becoming more negative. So because my number is getting closer and closer to the negative numbers, that is now a sign that this is negative acceleration. So really what you want to do is, or what you need to be able to figure out, if I give you a speed change, you should be able to tell me whether the thing is speeding up or slowing down based on whether the number is getting closer to zero or further from zero. You should be able to tell me whether it's positive or negative acceleration based on whether or not the number is becoming more positive or more negative. Another way of phrasing that is, if it's becoming less negative over time, that's positive acceleration. Or if it's becoming less positive over time, that's negative acceleration, which sounds really, really weird. And I understand if we have a lot of questions about this. Okay, so that's the qualitative part of acceleration done. That's the theoretical part of acceleration. And again, if it's a little tricky, it's easier for me to answer questions on that stuff. But let's get into the practical part of it, the actual quantitative measurement for acceleration and how we calculate it. So what we've got here is our formula. The formula for acceleration, you should immediately notice, is a little bit more complicated than the one that we had for uniform motion, our v equals d over t, all right? So remember that acceleration measures change in velocity, all right? So what we have to do here to figure out our acceleration is we have to actually use two separate velocities. We have to use our VF, our final velocity, basically what was the object's speed when it was done changing speeds, and the object's initial velocity. So where was it at the beginning? And what we're going to do is we're going to subtract those two things, okay? And then whatever we get as our answer for that subtraction, we then divide by how long it took for that object to change speeds. So we divide by the time. So what makes this formula a little bit trickier is we actually have one more variable than we did last time, all right? And on top of that, we're going to end up getting two different velocities in our problem. And as a student reading the question, you need to be able to figure out which one's the initial velocity and which one's the final velocity, all right? And so a lot of the time we have to look at context within the problems that we're trying to solve. So I find with this section that we really do need to do a good job of reading the question and figuring out what clues it's giving us, what bits of information it's giving us from the question. And sometimes it's not very obvious, and you need to know and assume certain things based on the wording of the question. So we're going to talk about how we can do that. And just a couple of quick little notes about gravity before we get any further is the units that we use to measure it. And we actually have talked about this a little bit before, but I said we would worry about it later. Well, it's later now, so we're going to worry about it now. If you think about the units that we're actually dividing here, we're going velocity divided by time. In acceleration, we're always going to measure acceleration in a unit that we call meters per second squared, which is a weird looking unit. That square in there really throws us off. It doesn't mean that we square the number or anything like that. It's actually just a part of the unit itself, okay? And what that actually comes from is the fact that we're going meters per second for our velocity, divided by seconds time, all right? So I'm going meters per second divided by seconds. When I do that, what you actually end up getting when you do this weird looking division here is meters per second squared, okay? So I want to talk a little bit about what this means. Really, when we think about it, acceleration shows us how quickly we're changing speed, and our unit reflects that. It's showing us how quickly our meters per second change every second. All right, when we actually just do the math, it ends up being meters per second squared. But really, you can think of it as how much your meters per second change every second. All right, and because this is our unit for acceleration, any velocity you get in any problem needs to be in meters per second. Any time that you get in any question needs to be in seconds. We are never, ever, ever going to measure acceleration in kilometers per hour squared. The reason that is when you think about what that means, that's like saying I'm going, how much are your kilometers per hour changing every hour, okay? Which, when you think about it in your car, when you change speeds, like when you go from, 50 kilometers an hour to 80 kilometers an hour, you don't take hours to do that. It takes seconds, all right? So we could measure it in kilometers per hour squared, but our numbers would be super, super small to the point where it's not a useful measurement for us. This is actually why we use meters per second in physics, is that it's more useful for us to understand how things are changing speeds every second versus every hour. All right, so before we look at example problems, I want to talk about a special case, which is gravity. All right, so it turns out that we know that gravity makes things accelerate. Like if you drop something off the top of a building, that object, that penny or whatever it is going to fall towards the ground. And as it's falling, it's going to move faster and faster and faster and faster. Gravity makes us speed up as we fall towards the earth. All right. Turns out, though, that the Earth makes everything accelerate at the same rate towards it. The gravity pulls down with a constant acceleration. And that acceleration is this magic number here that we're going to be using a lot over the next little while. It's one that is in your data booklet. You don't need to memorize it, but we're going to use it so much that it's going to become pretty common. All right, so gravity pulls or makes things accelerate at a rate of 9.81 meters per second squared. So what that means is every second that you fall towards the Earth, your speed increases by 9.81 meters per second, every single second, all right? Now, because it pulls things downward, it's important that when you're using this number, when we're doing problems, that you put a negative symbol in front of it when you're actually doing the math, okay? So keep that in mind. Acceleration is a vector quantity, which means if something is falling down, that number needs to be negative, otherwise it's going to throw off our units. So a trick here that comes up in problems all the time is if I ever talk about something like falling down or if I toss something into the air, we can always assume that gravity is pulling downwards, that there's an acceleration of 9.81 meters per second squared. And the problem won't necessarily tell you that, but it will say an object falls towards the Earth and then tell you some other bits of information. So you need to know that when something is falling, this is always the acceleration. Okay, so one of our first clues that we're going to look at in any kind of word problem, when you're trying to find numbers and try and figure out what bits of information it's telling you, if it's talking about something falling, then you use this negative 9.81 meters per second squared as your acceleration. All right, but let's get into some actual practice problems. These ones are going to be on page 15 of your book, right under where your acceleration formula is. Okay, so our first problem is the most basic type of problem. It's one where we don't need to rearrange our formula. All right, so we're going to look at the problem here and we're going to see what information it tells us. And it's really helpful in this section, way more than it was in uniform motion, to actually write down what the problem is telling you and what you're trying to find out. So this question here says, a naturalist observed a cheetah reach a speed of 19 meters per second from a standing start in a period of 2 seconds. What was the cheetah's acceleration? Okay, so we know just from that our acceleration is what we're trying to find. Okay. Then looking at my bits of information here, it says it reaches a speed of 19 meters per second. Okay, so that's the one speed that we're getting, the one velocity that we're getting. And we have to figure out whether that's initial or final velocity. And we can do that just by looking at the wording of the question. So it said we observed a cheetah reach this speed. That word reach tells us this is going to be the final velocity. Other times we might see something that says like a naturalist observed a cheetah you're going to see the word like to come up for final velocity. It might say something like it goes from this. To or reach is always going to end up being our final velocity. Okay, so our final velocity in this case, our VF, is going to be 19 meters per second. Okay. Next, it says it did that in a time of 2 seconds. The time is the easy one. So our time is 2.0 seconds. And then you might think, okay, but it's not telling us its initial velocity because those are the only two numbers in this problem, that 19 and that 2. But it does say in the problem that it had a standing start, or it might say it started from rest, okay? In those cases, what that's telling us is that our initial velocity, our VI, is just 0 meters per second, okay? The thing was sitting still to start with. And a note just for significant digits, which I know is going to come up, this 0 has an infinite number of decimal places. If something is not moving, it is moving exactly 0 meters per second. All right, so let's take a look at the actual question now. We know our formula is A equals VF minus VI over T. All right, we're already looking for acceleration. The problem is set up to find acceleration, so we don't need to rearrange the question here. We just need to plug our numbers in. So our acceleration is going to equal 19 meters per second minus 0 meters per second divided by our time of 2.0 seconds. When you put that in your calculator, you're going to go 19 minus 0. Do that first and then divide by 2. And when you do that, you're going to get 9.5 meters per second squared. Okay, because we're talking about acceleration. One thing I hope you notice in this question is that in the problem, it does not mention a direction at all. All right, so I'm not going to include a direction as part of this. If the problem gives you a direction, you should put a direction down. But if it doesn't, don't stress about it. Just write down what you get as an answer. All right, so that's our answer to the first question. Check our significant digits. 9.5 has 2 digits. These guys both have 2 digits, so we're good. Nice, easy question. All right, so we're going to take a look at this next problem. Now, this one's going to be a little bit trickier for us because it's not going to ask for acceleration this time, which means we're going to need to rearrange our formula, all right? And this formula is not as easy to manipulate as the V equals D over T one. There is no triangle that works with this one, for those of you that like that triangle, all right? So let's go through it here. Let's see what the problem is giving us and what we need to find out. So a car enters a highway traveling at a certain speed. Whatever that is, it's going to be our initial velocity. The car begins to accelerate at a rate of 2.55 meters per second squared. So obviously that's telling us the acceleration. Okay, so A is going to be 2.55 meters per second squared. Okay, and that's going to be positive, right? Because north is a positive direction. I'm just going to give myself a little bit more space here. From there, it says that after 5.5 seconds, so obviously that's going to be our time. Okay, 5.5 seconds. The car reaches a velocity of 28 meters per second north. Then it says, what was the car's initial velocity? Perfect. So we know that this is telling us final velocity because it says it's got that reach in there. So it reaches a velocity of this. Good clue that it's our final velocity. And then it's asking for initial velocity. So obviously the one velocity it's telling us is our VF. Okay, so VF is going to be 28 meters per second. Okay, and VI is what we're trying to find out. All right, so the formula that we have for acceleration is still A equals VF minus VI over T. okay? But this time I'm trying to solve for VI, so we need to rearrange this equation to get VI by itself. And I'll tell you right now, this is the hardest one for us to rearrange, okay? Of all the four things it could ask you in these problems, the initial velocity has the hardest rearrangement, right? But the first step to rearranging this formula every time, it does not matter what we're looking for, is to always multiply both sides of the equation by t. Remember, we're always trying to undo everything that's happening to our variables. And so right now, vi is being divided by t, so we want to get rid of that first, okay? And this is always our first step when we rearrange this. So I'm going to multiply this side of my equation by t, and I'm also going to multiply this side by t. This cancels out, and so what I get left with when that's done is t times a is equal to vf minus vi. Okay, and I just want to take a second to stop here. This is always what our formula will look like once we begin rearranging. As I said, the first step is always to multiply by t. And what this is telling you is that our change in speed is always going to be our final velocity minus our initial velocity. And what we're saying is time multiplied by acceleration is equal to how much our velocity changes. Okay, so that's a good way to think of this as for this next step, because this next step is the part where it gets a little bit odd, is that we need to get VI by itself, all right? And the issue that I have is currently I am subtracting VI. So normally we would say, oh, you just subtract VF from both sides. But what you would get, and don't do this, I'm going to change the color to red. What you would get if you did that is T times A minus VF is equal to negative VI. The reason that becomes a negative VI there is that this doesn't go away. If I just cancel out VF, this becomes 0. So I'm going 0 minus VI, which gets me a negative initial velocity. We don't want this. So what we're going to do instead is we are going to actually add VI to both sides of the equation. So if I add VI here and add VI here, it's going to cancel out on this side. And what I'm going to get is T times A plus VI is equal to my VF. Okay? Which still does not get us what we want. We still don't have VI by itself, okay? But now we have an easier rearrangement. So what I'm going to do is I'm going to take this T times A, and I'm going to subtract it from this side, and I'm also going to subtract it from this side. And so what I get when I do that rearrangement is this T times A cancels out on this side, and what I'm going to get is VI is equal to VF minus T times A. All right, this is now the formula that we want to use to solve this question. And I just want to go back and talk about this here. Remember I said that T times A is equal to how much our velocity changed. All right, so this formula actually makes a lot of sense in this idea that being that our initial velocity is equal to whatever our velocity is now minus how much it changed. So I'm going to clear off the slide here, and we're going to use this formula to solve this question. All right, here we are with a more cleaned up slide so we can actually do our problem. So we've got our formula. This is what we just figured out on the last slide. And if you're really confused on how I got this, that formula rearrangement, that's okay. What I found in the past is some students really get the algebra well and are fine with it. Other students who struggle a bit more with algebra, they'll just take the time to memorize this formula. So it's up to you kind of how you'd rather do it. I would prefer you to understand how to manipulate the formula, but if it didn't make sense, that's okay. The bigger thing is you're able to use the formula, all right? But I will not ever give you this formula. You need to know it on your own, okay? Anyway, let's add these numbers into our, substitute these numbers into the formula and solve our answer here, all right? So our initial velocity is going to equal our final velocity of 28 meters per second minus our time of 5.5 seconds times our acceleration, just giving myself some space, minus our acceleration, times our acceleration of 2.55 meters per second squared. Okay, when I do that work, what I'm going to get when I do all that math there is I'm going to end up with a final speed of 14, or initial speed, I should say, final answer of 14 meters per second, which has the correct number of significant digits. I need 2 significant digits because these numbers here only have 2, and that becomes our final answer. The one little thing that I'm missing here is that we need our direction, right? The problem tells us direction is heading north in both cases, so we need to say that our direction is also north. Had we, for whatever reason, ended up with a negative number here, that would have meant that our direction actually started off heading south. All right, that's why those positives and negatives are important to keep straight. All right, on to our next question. So let's just, again, take a quick look through it, see what it's giving us, and see what we need to find out. So an object is dropped from the top of a tall building. It falls for 30 seconds before hitting the ground. What is the final velocity before impact? All right, so we know right away that we're looking for final velocity. Okay, that's going to be our question mark. The tough thing about this problem is that it's only giving us one number, all right? Which means that the other two numbers that we need to have to use our formula aren't provided to us. That means we're going to need to do some digging into the wording of this problem to figure out if there's maybe more information than it's telling us, if we can actually assume those numbers, even if it's not giving them. All right, so the one that we do know is that our time is 30.0 seconds, okay? And then we have to figure out how we could figure out initial velocity, okay, because we're missing that, and we're missing acceleration. So a couple big clues. The first one that I hope jumped out from you right away is that this object is being dropped. All right, it's getting dropped from the top of a tall tower. That actually tells us our acceleration because remember, the acceleration due to gravity for anything that's being dropped is negative 9.81 meters per second squared. And it's important to use that negative, even though it didn't mention direction, we know that this thing is dropping. We know it's going to the ground, okay? So that means we do know its direction, so we want to make sure we keep that negative. And then if something is dropped, what that means is in that very split second, the second that it first gets let go, that like nanosecond of time, its initial speed is actually going to be 0 meters per second, okay? That thing is starting from rest, so that tells us our initial velocity. So this word dropped actually gives us 2 big clues. We know its initial velocity and we know its acceleration. The difference would be if something is thrown from the top of the tower, like if I throw something downwards, then its initial velocity will not be 0, right? Because it's going to have some velocity as it leaves my hand. All right, so what we're going to do now is figure out how to solve this equation. So we have A equals VF minus VI over t, but this time we're trying to find our final velocity, okay? So we're going to rearrange this formula again. This one's not so bad, okay? This doesn't have that weird little awkward step where we have to move the VI, okay? So as always, our first step is to multiply both sides of the equation by t, okay? What that does is it gets our t's to cancel out, and what I get as my new formula is the same one as before. T times A is equal to VF minus VI. Okay? From there, this one's much simpler. All I have to do to get VF by itself is the opposite of what's happening to it now. The only thing we're doing to VF is subtracting VI, so we're going to add VI to both sides. That's the opposite of subtraction, so I'm going to add VI to this side, which is exactly what I did in the last one. Okay? My VI's are going to cancel out over here, and so my new formula is going to be T times A plus VI is equal to VF. And you see here I've got VF by itself. It doesn't have a weird negative in front of it or anything like that. So that means that this is actually the formula we're going to use to solve this problem. I'm just going to flip it around so that the VF is on the left of the equal sign. All right, so here we are with our setup. We've got our time, we've got our acceleration, we have our initial velocity, we have our formula set up the way we want. All we have to do now is the easy part. We just have to plug the numbers in, all right? So our final velocity is going to be equal to our acceleration. Okay, important to keep that negative there. The time here was 30.0 seconds. And our initial velocity was just 0 meters per second. Okay, so we can kind of ignore that. So when I multiply those together, what I get as an answer is negative 294.3 meters per second. Okay, I can't keep that negative there. I have to turn that negative into a direction. We know what direction it is. And then I just have to double check my significant digits. I got 3 significant digits here, 3 significant digits here, so I need to round this to 3. So when I get my final answer, I have to report it as 294 meters per second down. Okay? And we know it's down because it's got that negative answer, which makes sense because if we drop it, it's moving downwards. That's why it's important to keep that negative with our acceleration. All right, so that one, not so bad to rearrange the formula, and then once we have the formula, it's easy. We can just throw it in our calculator and then just double check that our answer is the right significant digits and the right sign. All right, so another one that doesn't seem to be giving us all the bits of information, but when we read the question and we think about what that object would actually look like if it was moving, we can figure out some of the other parts to it. So it says here a ball is thrown upwards, thrown being key, with an initial velocity of 14.5 meters per second up. Perfect, there's VI. All right, I love when it just tells us in the problem that it's the initial velocity. Okay, and it's going to be a positive 14.5 meters per second because it's going upwards. Then it says, for how long would the ball travel upwards before reaching its maximum height? Kind of weird question. We haven't talked about distance at all with acceleration. It's not a part of the formula. It's actually not something that we can figure out from this formula. All right. So you might think, okay, well, how do I know what its maximum height is? That sort of thing. When you think about something, and you can try this at home, if you throw something up in the air and just give it a nice little toss, at the exact, I'm going to kind of draw it, as you throw it upwards, it's going to start slow, it's going to move with a pretty high speed as it leaves your hand. And by the time it gets upwards, it's going to slow down and slow down and slow down and slow down. Then it's going to turn around, it's going to fall back towards the ground. At this moment right here, at the very top, its maximum height, its speed is technically 0 meters per second. And we know that because it's slowing down, slowing down, slowing down, slowing down, slowing down, slowing down, stopping, speeding up, speeding up, speeding up, speeding up, speeding up, speeding up. Fun kind of cool fact here. Here it's got positive velocity, 0 velocity, negative velocity. We're going to talk a lot about that when we get into graphing acceleration. Don't stress about that so much today. The big thing we care about is that because it's asking us for the maximum height of this arc, what that means is that deleted everything. I knew that would happen. What that means is our final velocity that it's asking for is going to be 0 meters per second. Okay? Sorry. Feeling my old stuff. Okay, so our final velocity at the very maximum height is the very moment where its speed is 0 meters per second. Okay, and then because we're talking about something that's slowing down over time, we're talking about something being thrown into the air, that means the acceleration working on it is our good friend gravity, which is negative 9.81 meters per second squared. Okay, so anytime you're dealing with something falling down or something being tossed into the air, the gravity is always the acceleration is always negative 9.81. And then the question says, how long would the ball travel upwards? So it's asking us for time. And I think this is the easiest one to rearrange the formula for. You might disagree, but it actually ends up being kind of an interesting formula. So what we're going to do here is we're going to reconfigure our formula to solve for time. Here's our original formula. Okay, this time we're trying to find this. As always, our first step is to multiply both sides by t. We always want to get t out from underneath there because that t messes us up. Okay, the t's actually cancel out on this side. And so what I'm going to get is t times a is equal to vf minus vi. Okay, now, again, I want t by itself. All right, so all I have to do is undo what's happening to t. T is getting multiplied by acceleration. So what I want to do is divide by acceleration. So I'm going to divide this side by a, which means I also need to divide this side by a. My a's cancel out here. And so my final formula, when all is said and done, is t is equal to vf minus vi divided by a. The way I always remember this formula, if you're somebody that likes to memorize formulas, is that the t and the a just switch places, right? Up here, t was down here, a was over here. They just switch spots. The velocities stay the same. So now that we have our formula and we have all our work, let's go solve the problem. All right, so we've done all the hard work. Now the easy part, we're just going to plug all our numbers in and we're going to solve the problem. All right, so we're going to plug our numbers in. So here we go. Our final velocity was 0 meters per second. Our initial velocity was 14.5 meters per second upwards. And then our acceleration is negative 9.81 meters per second squared. So we're going to go 0 minus 14.5, which is negative 14.5, divided by negative 9.81. And when I put that in my calculator, what I get as a final answer is 1.48 seconds. A couple of just little notes about this. If I hadn't used a negative here, I would have got a negative time. And we've talked before about how we can't have negative times. So if you ever get a negative time as your answer, you've probably missed a negative somewhere, and you should go back and double check to make sure that it didn't mess you up too much. All right. We have our 3 significant digits, which is good because these guys have 3 significant digits, and I don't need to include a direction because time never has a direction. All right. So those are the 4 types of problems that I can ask. The biggest things to watch for are reading the question carefully to make sure you're getting all the clues out of it, because if it's not giving you the numbers, you need to figure out where those numbers are coming from. Typically, it's something to do with gravity. The other thing is watching which one is your initial and final velocity by looking at the context clues about things like it reaches this speed, it comes up to this speed, or it comes from this speed, or starting at this speed, and watching out for things starting at rest, because those are all initial velocities. Just things to be careful of. All right, so these are the 4 types of questions we can ask, right? If with any of these things, I can ask you for acceleration, final velocity, initial velocity, or time. These are the 4 formulas we ended up coming up with today. I would really prefer that you know how to rearrange the problem, but if you're somebody that likes to memorize these things, this is the kind of slide you want to know. The only the only formula you're provided with in your data booklet is this one here, and the more experience you have rearranging formulas, the easier it becomes. But this is just a nice little check-in so you can see, okay, there's only 4 ways to rearrange this problem or this formula. There are no other ways to do it. So I can only ever ask you for these 4 things, and this is how you would find them. All right, just kind of a nice little summary. So that's it. I know this is a bit of a longer lesson. I know it's a bit more of a confusing lesson, and I hope you guys come to me with questions on Tuesday and Thursday this week. All I want you to do this week is to practice acceleration problems. All right, we're not going to do anything else new this week. I'm still going to have online sessions on Tuesday and Thursday, but I'm giving you guys a ton of practice work. All right, so what I'd like you to do in your booklets is pages 15 to 18. That's a lot of questions. I don't expect you to do them all today. All right, but I expect you to get them done over the course of the week. I also have a boot camp sheet up on D2L, and I also have a practice question sheet also up on D2L. It's got 27 questions on it with the answers. Take the time to go through this. This is a harder skill than you've seen before in physics, and please come to me with questions as you go. All right, thanks guys. I hope you guys are doing great, and I can't wait to see you online.